Hey guys, and welcome back to another video. In this video, we'll be talking about curve sketching. Alright, so let's get right into it. Okay, so in previous videos, we talked about how the derivative can be very useful in helping us analyze the graph of a function. For example, the first derivative helps us determine where the function is increasing and decreasing, as well as local extrema of the function. And then the second derivative helps us find, the concavity of the function. And so curve sketching is basically putting all that information together, and then like the end result is, well, the graph of a function. All right. So basically, we can use all this information from like the first, second derivative of the function, as well as the function itself, to potentially sketch a graph of the function. All right. So in my opinion, this topic is best explained through examples, right? So let's go ahead and do example one. All right. So this is our first example. So we have f of x equals x to the fourth minus 12x cubed plus 48x squared minus 64x, and we want to sketch the graph of the function. Okay, so to begin with, let's go ahead and find our derivatives. So our first derivative, or before that, let's go ahead and factor our function. So f of x is factorable as x times x minus 4 cubed, all right? And so now let's go ahead and find our first derivative. F prime of x is equal to you get 4 times x minus 1 times x minus 2 squared, or x minus 4 squared. And these are just like product rule applications, right? So you just like differentiate x, then keep x minus 4 cubed, and then plus x times x minus 4, the derivative, right? But like, I'm just going to go ahead and list the derivatives here just for like sake of time. And then we have f double prime, again, just product rule on this. You get 12 times x minus 2 times x minus 4. Okay, good. So now there's like a list of characteristics that we need to know before we can sketch the graph of the function. So the first one is the intercepts. All right, so we need to know what the x and y intercepts are of our function. So let's go ahead and begin with that. So our y-intercept, that's just wherever x is equal to 0. So we just can evaluate f of 0, and from here you notice that all of our terms have x in it, so therefore f of 0 is just 0. So we have a y-intercept of 0, 0, namely at the origin. Okay, and then for our x-intercepts, we can just set our function equal to 0. So if we go ahead and set this equal to 0, we get a solution x equals 0. So 0 is a x-intercept. And then from x minus 4 cubed, we get x equals 4. So 4 is an x-intercept. All right, good. All right, so now that we have our intercepts, the next thing that we need to know is where the function is increasing or decreasing. All right, and so to do that, you need to find where the sign of the first derivative is negative and positive. All right, so let's go ahead and set our first derivative equal to 0. So we have 4 times x minus 1 times x minus 4 squared. That's equal to 0. And so you get x equals 1 and x equals 4. All right, so if we make our number line, like always, we have for x less than 1, so you can just like plug it in, right? So x minus 1, if you plug in x less than 1, so let's just say 0. 0 minus 1, that's a negative number. 0 minus 4, that's also negative, but you're squaring the second term, so that becomes positive. So you have a negative number times a positive, that's a negative overall. So it's negative for x less than 1. All right, in between 1 and 4, let's just say like 2, you have 2 minus 1 is positive, and then 2 minus 4 is negative, but you square it, so it becomes positive. So you have positive times positive, which is positive. And then finally, for x greater than 4, you have like 5, let's just say. So 5 minus 1 is positive, and 5 minus 4 is positive, and squaring is also positive. So you have positive overall. All right, good. So now it's so f prime is negative on negative infinity to 1, so it's decreasing on this interval. Okay, so I'll just add it right over here. So we're decreasing from negative infinity to 1, and we're increasing everywhere else. So we're increasing 1 to infinity. Because at x equals 4, yes, you do have a critical point there, but notice that the derivative doesn't change signs. it remains positive. So therefore, it's increasing for all x greater than 1. Okay, good. And so because the derivative doesn't change signs at 4, we don't have a local extrema at 4. But the next step is to determine the local extrema of our function, right? So at x equals 1, our derivative is going from negative to positive. So then by the first derivative test, as we learned, that means that we have a local minimum at x equals 1, right? And you get a local minimum of 1, negative 27, all right? And then as for local maximum, at x equals 4, it stays positive, so we don't have any local maximum, right? So I'll just say local max, there is none. All right, very good. All right, so next we need to determine the concavity of our function. All right, so where the function is concave up and concave down. So to do that, we need to set our second derivative equal to 0. And so we get x equals 2 and x equals 4. So these represent the possible points of inflection, but we'll get to that in a second. And so let's go ahead and make our number line now. So we have 2 and 4. This is for f double prime now. So for x less than 2, again, you could just like check in each of these. So like when this factor is very nice to check. Like you don't have to plug everything in. You can just like see the sign of each factor. So for example, x less than 2, so let's just say 0 again. 0 minus 2 is negative. 0 minus 4 is negative. But then we have negative times negative, that means, so that's a positive. So it's positive for x less than 2. In between 2 and 4, so let's just say 3. 3 minus 2 is positive, but 3 minus 4 is negative. So we have positive times negative, which is negative overall. And then for x greater than 4, let's just say 5. 5 minus 2 is positive, 5 minus 4 is positive, so we have positive overall. All right? So what does this mean? So this means that our graph is concave up on negative infinity to 2 and 4 to infinity. Okay? And then we're concave down from 2 to 4. All right, good. So now let's determine possible points of inflection. Well, we know that the second derivative changes signs at both 2 and 4, so both of those points must be points of inflection. And let's go ahead and find what those are. So at 2, we have a point of inflection at 2, negative 16. All right, so you just like find f of 2 and you should get negative 16. And then at 4, we already found that f of 4 was 0, right? We have an x-intercept there. So we have a point of inflection at 2, negative 16, and at 4, 0. All right, good. And so then the final thing that we need to know in order to graph this function is the end behavior. And I'll just tell you that the end behavior is only necessary for polynomial functions. Once you like graph rational functions and radical functions and all that, the asymptotes are like what basically replaces the end behavior. All right, let's go ahead and find the end behavior of this function. So if you remember from our pre-calculus videos, and if you haven't checked that out, definitely check that out. Very helpful, right? But all we need to know to determine the end behavior of a polynomial function is the degree of the polynomial and then the sign of the leading coefficient. So for example, in our case, we have a 4th degree polynomial, so that's an even degree, and then our leading coefficient is positive. And so when I covered end behavior in my pre-calculus series, that meant that the end behavior as x approaches positive and negative infinity was infinity in both cases. So our end behavior is that x approaches positive and negative infinity, right? Our function is always just increasing without bound. Okay, nice. So now that we have all of that information, we can go ahead and graph the function. All right, so I have sketched the coordinate axes here. So let's go ahead and graph this function. So to begin, let's start with our intercepts, right? So we have a intercept at 0, 0, x and y. So we know that the graph intersects at that point. And then we have an x-intercept at 4, 0 also. So each of these ticks represents 1. So we have 1, 2, 3, 4. So we have x-intercept right over here. All right, good. Next, let's see. We have a local minimum at 1, negative 27. All right, so I'll just say negative 27 is right over here. And so that means that we have a local minimum at this point right over here. All right, local max, we have none. Let's see, points of inflection. So we have 1 at 2, negative 16. So we'll just say that's like right about here. All right, we'll just say this is negative 16. And then 1 at 4, 0, but that's already graphed. And then our end behavior, just like it's increasing without bound, right? So a point of inflection at this point, so that means that our concavity changes. So let's see what the concavity is before. So from 2 to 4, it's concave down, right? So, okay, so from negative infinity to 2, it's concave up. So that means that this whole portion of the graph right here is going to be concave up. And then from 2 to 4, so from here to here, it's going to be concave down. And then at 4, 0, we have another point of inflection, and it's concave up after that point. So it's going to be concave up. Okay. So yeah, that's that. We have a minimum here, so that means that our graph should be concave up like we already mentioned. So it's going to look something like this over here. All right. And yeah, it's decreasing from negative infinity to 1. So here is like going to decrease, and then it's increasing from 1 to infinity. All right. So with all this information, we have determined that a graph should look something more or less like this. Right. So it's increasing here, it's concave up, hits this point of inflection. So now we're changing concavity to concave down until we reach this point, but it's still increasing. All right. So then we're concave down, concave down. All right. We've hit this point. Another thing I want to mention is that at 4, 0, we had a critical point. Remember, at x equals 4, our derivative was equal to 0. It's just that the sign didn't change. So we didn't have a relative minimum or maximum. But that still does mean that the slope here is like instantaneously 0. So we should draw like a horizontal piece of the graph here. Like it's horizontal, and then it goes back to concave up. All right. And it just keeps increasing as according to our end behavior. And then here we have a local minimum, and it's concave up, and it's but like for x less than 1, it's decreasing, right? So it's like decreasing, and it goes to this point. So it's probably just like a straight line down like this, straight curve as such. Ooh, I didn't really make it intersect there. Let me just try that again. All right. All right, that's a rough sketch of what the graph should look like. All right. Like it goes down, comes here, changes concavity to concave down, then changes concavity again, concave up, right? So this is roughly the graph of y equals f of x. All right, very good. Let's move on to our next example. All right, so our next example, we have f of x equals 3x over x squared minus 1. All right, so again, let's first go ahead and find our derivatives. So we have f prime of x equals, so remember, this is just like a quotient rule application. So you just do like low d high minus high d low all over the square root of what's below, right? But then again, for the sake of time, I'm just going to go ahead and write our derivatives here. So you have negative 3 times x squared plus 1 all over x squared minus 1 squared. Because at this point, you should be pretty comfortable with taking these derivatives yourself, right? They're not too bad. And then f double prime of x, again, just another quotient rule application. You should get, or you get 6x to the 5th plus 12x cubed minus 18x all over x squared minus 1 to the power of 4. Okay? All right, good. So again, let's first start with our x and y intercepts. So our y-intercept, that's just evaluating f of 0, and so that's, we have 3 times 0, which is 0, all over 0 minus 1, so that's negative 1. So we have 0 over minus 1, so that's 0. So we have a y-intercept at the origin. And then for x-intercepts, we just set this equal to 0. So if you do that, you get that 3x is equal to 0, so that means the x is equal to 0. So you have a x-intercept also at 0, 0. Okay, good. All right, next we need to find our asymptotes in this case because we're dealing with a rational function. So now we need to find our vertical and horizontal asymptotes. So for our vertical asymptotes, remember, that's just wherever the denominator is equal to 0. So if we set x squared minus 1 equal to 0, so this factors as x plus 1 times x minus 1. So we have vertical asymptotes at plus minus 1. All right. And then horizontal asymptotes, that's just looking at the degree of the numerator compared to the degree of the denominator. So we have degree 1 over degree 2. So if the degree of the numerator is less than the degree of the denominator, that means that our horizontal asymptote is just y equals 0. Right? So there you go. All right, good. All right, next let's go ahead and find our local extrema as well as where our function is increasing and decreasing. All right, so to do that, we need to set our first derivative equal to 0. So we have, let's see, negative 3 times x squared plus 1 all over x squared minus 1 squared equals 0. Right? But then real quickly, notice that x squared plus 1, that's always positive. Okay, and then x squared minus 1, that could be positive or negative depending on x, but then you square it, so now this is also always positive. So if we just ignore the negative 3, this fraction is always positive. But then now you have the negative 3, so then that means the whole fraction is always negative. So this expression, this quantity right here, is always going to be less than 0. All right, so what does that mean in our case? So that means that, first of all, we don't have any local extrema, right? Because the derivative isn't equal to 0 anywhere. And it's undefined at plus minus 1, but we already have vertical asymptotes there. All right, so no local extrema to begin with. All right, so local extrema, none. And then as for increasing, decreasing, we just determined that our first derivative is always negative, always less than 0. So that means that our function is decreasing over its whole domain. Okay, so decreasing. So but the thing is, in this case, the domain is not just negative infinity to infinity. We have those asymptotes. So the domain, it's decreasing from negative infinity to negative 1, negative 1 to 1, and then 1 to infinity, right? But then it's never increasing. All right, good. All right, so now let's determine the concavity of our function. So to find our concavity, we just have to set our second derivative equal to 0 now. And so that means that this expression in the numerator, we have 6x to the 5th plus 12x cubed minus 18x is equal to 0. We could divide both sides by 6 to get x to the 5th plus 2x cubed minus 3x equals 0. And then we can factor this. So this factors as x times x to the 4th plus 2x squared minus 3. All right, so you factor out the x. And then this actually also factors. You can factor it as x squared minus 1 times x squared plus 3. And then now notice that x squared minus 1, you have a difference of squares. So that factors even further. So you have x plus 1 times x minus 1. And then we have the x squared plus 3. All right, good. So from x squared plus 3, again, that term is always positive. So we don't get like any real root from that. So we can ignore that. But from these three, we get x equals negative 1, 0, or 1. Right? So those are our possible, or those are like the intervals that we have to test. Right? So let's go ahead and make our number line. So we have 0, minus 1, and 1. And this is for f double prime. So for x less than negative 1, you get that the second derivative is negative. All right, for negative 1 and 0, in between there, you have that it's positive. In between 0 and 1, the second derivative is negative, and then for greater than 1, it's positive, right? So in this case, you just have to like substitute values in each of these intervals into f prime, or f double prime, I mean, sorry, and just like, determine the sign. But yeah, you get this. So then this means that our function is concave up wherever the second derivative is positive, right? So that means on the interval from negative 1 to 0 and then 1 to infinity. So it's concave up negative 1 to 0 as well as 1 to infinity. And then we're concave down from negative infinity to negative 1 and 0 to 1. Okay. All right, very good. And finally, our points of inflection. Well, so our points of inflection. So actually notice that at plus minus 1, our function isn't defined, right? We have vertical asymptotes at those 2 points. So at negative 1 and 1, even though the derivative, the second derivative, changes signs, we don't have inflection points there. Instead, we have asymptotes. So therefore, the only point at which we do have a point of inflection is at 0, and that point is 0, 0. All right, so we have a point of inflection at the origin. All right, but yeah, that's all the information that we need to graph this function. So let's go ahead and graph this function now. All right, so I went ahead and drew the coordinate axes, and so let's go ahead and graph this function now. So we have x and y intercept at the origin, as well as a point of inflection. So let's go ahead and plot that point. We have vertical asymptotes at plus minus 1. So this is negative 1, this is 1. So let's go ahead and draw in our vertical asymptotes using a dotted line. All right, so negative 1 and 1. And then we have a horizontal asymptote at x or at y equals 0, but that's just the x-axis. All right, so you can label it if you want. Y equals 0. All right, good. So local extrema, we have none. We're decreasing over the whole interval domain. Concave up. Okay, so we're concave up from negative 1 to 0. So on this portion of the graph right here, between negative 1 and the y-axis, we're concave up. So it's probably looking something like this on this, right? So looking something like that. And then we're concave down on 0 to 1. So from here to here is 0 to 1. And that makes sense because 0 is a point of inflection. So it changes concavity from here to being concave down. All right. So that's what that middle part looks like probably. All right. And then for x greater than 1, we're concave up and we're decreasing. So that means that it looks something like this. Right. And then for x less than negative 1, negative infinity to negative 1, we're concave down, but we're still decreasing. So it looks something like this, most likely. Ooh, let me draw that a little bit better. There we go. All right. So yeah, this is a pretty good sketch of the graph of y equals f of x. All right. All right, so now let's move on to our final example. All right, so for our final example, we have f of x equals x over the square root of x squared plus 2. Okay. So again, we can go ahead and find our derivatives. So our first derivative, f prime of x, is 2 over x squared plus 2 to the 3/2 power. And then f double prime of x, we have we have negative 6x over x squared plus 2 to the 5/2. And again, this is just like product rules. Like this is like you have x times x squared plus 2 to the negative 1/2, and then you can just apply product rule to this function. Okay, good. So now, again, our first step in graphing these, we have to find our intercepts. So our y-intercept, that's just when x is equal to 0, and so you have f of 0 is equal to 0. This 0 squared plus 2, that's always positive. Like regardless of what x is, this term is always positive. So we just have y-intercept of 0, 0, and then x-intercept also is just 0, 0. Okay, good. Then for our asymptotes, so we have vertical asymptotes and horizontal asymptotes. So for vertical asymptotes, that means that the denominator is equal to 0, so it's undefined there. But remember, I just said x squared plus 2 is always positive, right? And so you have the square root of a positive number, that's also always positive. So that means that we have no vertical asymptotes. And then as for horizontal asymptotes, so as x like just gets bigger and bigger in like magnitude, right? Then x squared plus 2 can be approximated by x, right? Because if you have like a really, really large number here, x squared, adding 2 to it doesn't really affect it. So then we can approximate this as x over the square root of x squared for like large x. Square root of x squared is equal to absolute value of x. Okay. So then depending on the sign of x, this is either equal to positive 1 or negative 1. All right, so this is equal to plus minus 1. And so therefore you have a horizontal asymptote at plus minus 1. So you have horizontal asymptote y equals plus minus 1. All right. Good. All right, so now let's move on to our like local extrema and where the function is increasing and decreasing. All right. So to do that, we have to see where our first derivative is equal to 0. But then notice that this thing is always positive again, right? Because we have 2 over x squared plus 2 to the 3/2. That's always greater than 0. So this means that local extrema, we have none. None. And because our first derivative is always positive, that means that our function is increasing over its whole domain, which in this case is negative infinity to infinity, right? So we're increasing over our whole domain, negative infinity to infinity, and we're decreasing never. Okay, good. So now concavity. All right, so we need to find where this function is concave up and down. So to do that, we have to set our second derivative equal to 0. And so then this simplifies to negative 6x equals 0, which means that x is equal to 0. So let's go ahead and build our number line now. So we have 0, and this is for f double prime, right? So for x less than 0, we have that you have a negative number, right? So x squared plus 2 to the 5/2, like I said, that's always positive. So we only care about what the numerator is. So if you have like a negative 6 times a negative number, that's positive. So then the whole thing is positive. So for x less than 0, it's positive. For positive x, we have negative 6. So we have a negative number times a positive x. So that in total is going to be negative. And then divided by a positive number, that's still negative. All right. So there you go. So that means that we're concave up on negative infinity to 0, right? And we're concave down on 0 to infinity, right? And then that means that we have a point of inflection at 0, which is just the origin, 0, 0. All right, good. So now we have all the information that we need to graph this function. All right, so here are the coordinate axes. So let's begin graphing. All right, so we have an intercept x and y at the origin at 0, 0. All right, so let's go ahead and plot that point. And then we have no vertical asymptotes, but we have horizontal asymptotes at plus minus 1, right? So let's go ahead and sketch those in with a dotted line. All right, so this is y equals 1. This is y equals negative 1. All right, and then we're always increasing. And so now let's look at our concavity. So from negative infinity to 0. So before x equals 0, we're concave up, and we're increasing. So that means that our graph looks something like this, right? We're approaching the asymptote and we're increasing concave up. So it should look like that. And then we have a point of inflection, so we change concavity to concave down. We're still increasing though, and so we should look something like this. Alright, so this is the sketch for y equals f of x, where f of x equals x over square root of x squared plus 2. Okay, good. So yeah, that pretty much wraps up this video on curve sketching. If you found this video helpful, please make sure to leave a like and don't forget to subscribe. I'll see you guys in the next video.